It's great to be back at USC. I spent a few years here, and I'm going to start the presentation with some of the studies that I worked on during my time at USC. I'm an assistant professor at Virginia Tech, and we do focus on data-driven operational analytics and intelligent environment operations. And I'm happy that I'm going after the presentation from Olga and others, because it's going to build the case, on top of the rest of the presentations. So again, in general, I'm focusing on adaptive operations that help us improve the operations in buildings and cities and different domains. This presentation has a more specific focus on buildings and connected homes and buildings. And the motivations, we all know about these numbers and motivations, and there are a lot of efforts to reduce energy consumption, and specifically, in addition to reducing energy consumption, to balance the distributed energy resources across buildings. My research in general focuses on two areas of intelligent environments and demand-side management, or what I refer to as city-scale energy analysis or energy management. And I'm going to talk about case studies for each one of these few case studies. So we are actually looking into different human-building interaction modalities, and we are trying to actually quantify those, create models around them, and use those models as representations for human dynamics in buildings and cities, and use those for better operations. And we actually have created this taxonomy and tried to actually come up with this ontology of different aspects of human building interaction with a specific focus on energy applications in this case, and how we can actually leverage this to use energy to improve energy analysis. So when I started, actually, when I was doing my PhD, we started actually looking into how we can integrate human perception into the buildings, and the motivation was actually, this is a study that we conducted that in the fall of 2010 in Los Angeles. We observed that a lot of people are actually complaining about being cold and cool in the buildings, and we were also cooling down at that time. Again, we observed that in the summer, we have also a lot of complaints about being cold in buildings. Again, we are cooling down. So we are using a lot of energy to cool down the buildings, 43% HVAC systems, and we're making a lot of people unhappy. So we are inefficient from different perspectives, from service delivery, from energy efficiency. And this is not specific to USC, so because I graduated from here, I want to say that this is a global problem. This is not a USC issue. This is a study that was conducted in US, Canada, and Finland, and most of the people were unhappy with the thermal comfort in the building. So where the problem comes from? So the control system in buildings is actually very rigid and very limited. So we have a very single degree of freedom in communicating with buildings what we want in the building. So, and humans basically have no say in the system. So how do we quantify thermal comfort? We actually look into some environmental factors and human factors. And it is actually a famous model. It's called PMV model, or predicted mean vote, that was developed years ago through controlled studies to actually create a standard for building design and control. But over the years, because of the developments of information technology, we can actually go beyond this and integrate the human factors. So right now, or in the conventional control strategies, we are missing the human perception or human input to the system. So we actually looked at this issue, and we wanted to see how we can actually integrate human input. So we started developing a framework for participatory sensing-based control of buildings. Basically, we created an app with certain interface, and we enabled this with a back-end learning system that helps us learn the behavior or the preferences of people across the time as they interact with this environment. And also, we had a control component into it that it was reacting to the changes that people were requesting. And by doing so, we implemented this framework in one of the buildings on campus. Actually, this is the building that is basically the School of Public Policy. To be honest, I forgot the name of the building, so what was the name again? Yes, okay, thank you so much. So we implemented this system, and we actually observed that it was very effective in improving the comfort of people over a course of 2 to 3 months. And we were, at the same time, we were actually able to reduce energy consumption by around 40%. And this is actually a reflection of airflow reduction into the thermal zones. So this was basically the foundation for what I started actually after this, that we managed to actually improve user integration, but we're still requiring a lot of input from human. And these apps are basically constantly asking for people to provide feedback. And we have seasonality, so we need to actually be able to reflect a more distributed or distributed sensing. So I started actually looking into seeing if we can actually use ubiquitous computing devices and the amazing computational resources that we have, mobile resources that we have, to enable human body as a sensor proxy for measurement without actually asking for people to contribute data over and over again. So we started looking into this spectrum of different technologies, from non-intrusive to disruptive intrusive, from less effective to highly effective. And we actually came up with these four metrics of technology that could be actually useful. So we thought that the technology should be ubiquitous, non-intrusive, applicable, and sensitive enough for control of air conditioning systems. And based on this, we actually started looking into potential alternative technologies that we could enable such applications. So the first thing that came out to my mind is that we have a lot of cameras around. We're sitting in front of computers, and we are actually looking, the camera is actually looking at our face. We have mobile phones. So if we look at the thermophysiological response of human body, we actually use a few mechanisms to control the thermal or heat exchange between the environment. One of these are actually adjustment of the blood flow to the skin surface to actually help us regulate the thermal condition and keep the core body temperature. We actually looked at this and we said, so can we leverage this as a source of information through RGB cameras for detecting thermal comfort? And this is actually using image magnification, a very famous approach that has been developed at MIT. And we developed a framework, an algorithmic framework. I'm going to skip the details of these algorithms, but the bottom line is that this algorithm actually uses the sensing or the images from the camera. It takes the faces, isolates the skin, and then it starts looking into different color spaces and characteristics to identify the difference between blood flow variations under the skin. So this is some of the information from different color spaces, Cohen's channel, red channel. Again, I'm going to skip the details. But as I said, so we actually address the ubiquity and non-intrusiveness. I'll get back to this non-intrusive aspects of it because of privacy issues. But one of the things that we wanted to do is to actually be able to use this in variable thermal conditions, when we have actually transient between cooler to warmer temperatures. And that's actually add to a lot of challenges because the thermoregulation process is not going to be stabilized or stable at the time that we are actually moving across different temperatures. So we actually came up with this framework that helps us reduce the noise from different artifacts, motion artifacts, and similar things. This is basically an adaptive filtering that actually isolates the noise and captures the clear signal of the blood flow variation. And this is actually the result for a few of the studies that we conducted actually across different temperatures. And as you can see, it can actually detect the trend. So we can use the RGB cameras of a normal webcam to capture the trend of temperature changes from just looking at the human face. Of course, this has limitations. Privacy concerns is number one. There are different variations in color, in skin color, differences in luminance of the room, and similar challenges. So we are still looking into these to actually enable it in a larger scale, and we are also looking into using the same technology and use on wearable devices like smartwatches to use those sensors for measuring these variables. We're also looking into alternative solutions. As you mentioned, actually, we are using Doppler radar sensors for detecting thermal comfort, and we've had some success in actually quantifying thermal comfort based on the volume of, or inhalation, exhalation, depending on the volume of exchange or air exchange. Looking into heat flux sensors, as again, we're looking at heat flux sensors as wristbands for smartwatches, and we had developed models. But beyond comfort, there are a lot of other forms of interactions that people actually have. And this is actually a case study from larger scale, city scale study that we're looking into how we can actually use interactional behavioral patterns to quantify habits and behaviors of interacting with buildings, appliances, and analyze them for creating flexibility capacity in different buildings and using that information to engage fewer people in the process of balancing demand and generation. So, of course, again, this is actually, the focus is to balance between the challenges of addressing peak time, variability in renewable resources, and making sure that we can always keep the balance into the system. So we're looking into home energy management systems. These are the automation systems that control certain number of loads, like deferrable loads, like washing machines, dryers, and also electric vehicles. And also under the constraints of preference range, how people actually prefer these to actually take control. As mentioned, Leon actually mentioned this morning, that it's important how to consider the spectrum of variation between complete control. So looking into, I'm actually going to skip these quickly. So looking into this, we actually looked into Beacon Street data for over 400 houses, and we actually created a statistical metrics of user interaction with appliances. This is actually the data at appliance level. And we created this framework of scoring people's behavior in rooms, in houses, using frequency of usage, peak time usage, and consistency of usage. I'm not going to get into the details of the statistical formulas, but this is actually an example of EV charging behavior. And we could actually use this to rank people based on their potential to getting engaged in load balance across a community. And we tested this for tackling the peak load without actually creating a rebound effect, which is actually another peak after the fact. And we actually observed that here in this study, by using these scores, we can actually engage a small portion of people. In this case, we are actually engaging 20% of the entire community, or we were able to actually reduce 67% of the charge at that point. So this is actually helping us to achieve a better performance in operations. Of course, these studies are actually looking into quantifying human behavior, but an important part from my perspective is actually in adaptation thinking and how buildings can actually play a role in adaptation. So at this point, buildings are very rigid. We're sitting here, all of us have to actually tolerate the same thermal environment. There is this thermal environment cannot actually address different variations of people in this room. So it is important, and to that end, we are actually conducting a number of studies on creating artificial intelligence, robotic agents in buildings that actually can help achieve these objectives. And by that, I'd like to thank you for your attention. And this work that I presented, the DOE support is for the USC studies that we did, and the rest is actually supported by NSF and Regional Tech. Thank you so much.